joined before we start. In the meantime, feel free to post your greetings in the comment section. We will wait for 2 minutes. After that, we will start. If you guys have any question, you can write in comment section. So we are starting. Hello everyone, welcome to our live session. My name is Abdullah and I am your host. Today marks day 8 of our series. This is Math Club event organized by TFUZ Ghaziabad. We are thrilled to have a very special guest, Dr. Anuprati Bansal, with us. It is my great pleasure to introduce Dr. Anuprati Bansal. Dr. Bansal holds a PhD from IIT Delhi and is the lead of TFUG Jaipur. She is also working as a data scientist at Lumic. Dr. Bansal is a prominent academic and leading figure in the tech community, known for her significant contribution to the field of optimization and machine learning. Today, Dr. Bansal will be guiding us through unlocking potential of gradient descent, a journey to optimization. We will dive deep into the fundamental of gradient descent, explore various optimization techniques, and see practical real-world application. Without further ado, please join me in welcoming Dr. Anuprati Bansal. Dr. Bansal, the floor is yours.
So thank you everyone. Um, Thank you all the uh, participants or attendees who are listening to us. Thank you for joining us on Saturday. And I would also, before we start, I would like to extend my thanks to Akash and Abdullah, whole team of TFUG Ghaziabad for taking this initiative. Because whenever we talk about machine learning, mathematics is the fundamental of everything. And in today's presentation, I have taken one topic related to gradient descent. This gradient descent is, you can consider it as a fundamental of how this whole learning, deep learning, and AI thing works. So, so let's start the presentation. I am turning my video off so that there is no bandwidth issue, and we will take. If you can, if you think that I have kept my presentation very basic, so but even if you think you have any question, just write it on the comment section. I will take all your comments at the end of the session. So anyone can tell me whether my screen is visible? Can someone unmute and tell me if my screen is visible to you?
Yes, yes, your screen is visible.
Okay, okay. Thank you so much. So before wasting any time, I want to start directly with what is the gradient descent and what is today's session all about. Before we start, I would like to acknowledge that the most of the slides and most of the content of this presentation are based on lecture 3 uh, of deep learning course taken by Professor Mitesh Khapra at IIT Madras. The content is inspired and taken from his course, but I have kept it very simple so that if even if you're not very hardcore person who understand, or you don't have any uh, understanding of mathematical concepts behind a machine learning or deep learning, you will be able to understand it. I'm starting from the very basic. So I have kept this presentation very short. The first segment of the presentation includes intuition behind gradient descent. uh, what is the gradient descent, why we need gradient descent, and why this has become a core of all the machine learning and deep learning algorithms we see today. And in the second part of the presentation, I am trying to explain the mathematics behind the gradient descent. So let's start with the intuition behind gradient descent. So I am assuming that you all have some idea about neuron and perceptron in general. Even if you don't know, just want to summarize it for you. Suppose this is my neuron. You see this, you must have seen this kind of neural network. Okay. This single entity, we call this single entity as neuron, and we also can call it as a perceptron. Okay. All these units, all these neurons work in a similar fashion. And if I talk about very fundamental part, I can divide this neuron into two components. The first, this is suppose input, this is my output. Okay, and this is my neuron. What do I mean by x1, x2, x3? So let's take one example. I will take this example in all the topics to discuss about the intuition and the mathematics behind the gradient descent. So let's take an example like whether I would like to watch a movie or whether I like or dislike a movie. So why is my decision whether I like a movie or whether I don't like a movie? Now, on what basis I'm deciding whether I like a movie or not? It can be who the actor is, who the director is, how was the story, and there can be other parameters as well. So this is my input, x1, x2, x3. In another example, if you want to take whether I want to predict or whether I want to predict how much will be the rainfall tomorrow. Okay, so this y is the intensity value of rainfall. It can be 10 mm, 100 mm, or whatever. And x1, x2, x3, these are the inputs on the basis of which I will decide the intensity value of tomorrow's rainfall. X1 can be temperature, it can be humidity, it can be pressure. And on the basis of these inputs, I will try to learn or try to get the intensity value of the rainfall. Okay. So this is input and output. Now, when I am talking about neuron, it also consists of two parts. First is the summation part, and second is the sum function. Let's talk about this function later on. So, whenever I'm talking about the intensity value, this x1, x2, x3 has some weightage. Maybe temperature is more important or humidity is more important rather than pressure in predicting the rainfall. Or if I take a movie example, whether I like a movie or dislike a movie, maybe for me, the actor is more important. If the actor is suppose Ranveer Singh, I will definitely go and watch the movie. But suppose it is some other actor, I will not go and watch a movie. So there can be a weightage of certain input parameters as compared to other parameters. So each of these inputs are associated with these weights. There is another term which is called as bias. I am not talking about it because I'm assuming you have some idea. It's just a basic thing which I want to s- like revive you, give you a it's just kind of a revision kind of thing, so that you don't lose me in between. Okay, and you understand all the concept. So this neuron is first part is summation. So first part is it's the weighted sum of all the inputs. Okay, and this f is some activation function. So suppose this I'm representing, this sum I'm representing with z. So my y is 1 upon 1 plus e raised to power minus z. This is my sigmoid and activation function which I most commonly use. So after this z goes to y, and then it gives me z goes here in this equation and it gives me the final output value. Okay. So this is about the basic neural network. Now, in if I talk about the basic supervised learning system, we need to learn these weights. How would I know that maybe in certain cases, even if the actor is not Ranveer Singh, but story is good, maybe director is someone else, I will go and watch the movie. If it is an animated movie, I will go and watch the movie. So, what are the parameters and what are the weights? On which parameters, to which parameters I am giving more importance, and to which parameters I am giving less importance. So, we need a mechanism to learn these weights. Okay, and in in this presentation I will consider the sigmoid activation function. There are other activation functions as well, like ReLU, leaky ReLU, um, but we will not consider that. So this is the whole thing that we want to learn these weights. Now we want to learn the weights, but before understanding, and we need to learn these weights automatically. Okay, how to learn these weights? For that we need an algorithm. But before discussing that algorithm, I would like to uh, explain you the concept of error. What do we mean by error? So suppose this is the my classic example where blue are some sample points. Maybe it is representing whether I like a movie or dislike a movie, and this red, suppose blue represents I like a movie, and red represents I dislike a movie. Okay. Now, if I talk about single neural network, single perceptron model, so perceptrons were not able to deal with the non-linear data. What do you understand by non-linear data? Suppose I have this example where maybe circles are there. Sorry, circles are there and some crosses are there. I cannot solve this problem using a straight line. I cannot solve this problem using a I cannot solve this problem using a straight line. I need some f- boundary like this in order to separate these circles and these stars. Okay. But right now I'm considering a very simple a simple example where I can segment, or I can use the perceptron model where I can have a boundary where which gives me a almost a good separation between two types of data points, red and blue. Now, what do we understand by this almost a decent separation? Because if I see, there are certain red points, there are three red points on my on right hand side, and there are three blue points on left hand side. So separation, this boundary, though it is a good approximation and it's able to classify these two categories, but there are little bit misclassification, I can say. And in most, so here we are not getting the zero error because it will, due to these misclassifications here and here, I will not get zero error because I'm not able to classify all these examples correctly. There are 6 sample points which I was not able to classify properly, and there was an error for this. So there is no zero error here, but this is acceptable in most of the real world cases. In most of the real world cases, we don't get zero error, but we get a almost close to zero error. Okay. So, so this brings us the a machine learning setup which has the following components. Let's discuss all these components one by one. First, let's understand this data. What is this xi, yi? Xi, as I have given the previous, these are my data points. So if I talk about this movie example, so these are the parameters, like who is the actor, who is the director of the movie, what is the genre, and the corresponding label for this. Okay. So this is a x vector which is of Rm. So this is a vector of m length. And this is my y. What is the output? Whether I like a movie or, and instead of like or dislike, I can also take a rating. Like how much rating I would give. I would give 3 rating, 4 rating, 4.5, whatever. So this y is my rating. Okay. And this belongs to R. Okay. It's a single valued output right now. It's a scalar, we can say. Okay. So we have different examples. This can be rainfall parameters. This is the amount of rainfall. This can be your if I take an example of whether the person, how much loan will be approved to a person. So there can be different parameters on the basis the amount will be decided. The one parameter could be like what is the salary, if the person, how much loans the person has taken previously, and what are the liabilities, other loans, and so on and so forth. Okay. So here, in order to get the value of y, I this y depends on these value of x. So here I am writing this y depends on x. If I say what is the box office collection or what is the IMDb rating, so it depends on all the movie characteristics. Okay. So this F is a function I, which provides me a relation for x which gives me the value of y. Now, if I know this function, if I know this function, there is no problem at all. I will definitely get the ratings. If I know this function, how x is related to y, it's no problem. For example, it can be like this: basic x, y is just a square of x. So this is my function. It can be a more complex form as well. It can be something like this as well. Okay. So what is this function? I don't know. So, but if I know this function, it's very good for me. Okay. And I am saying that there is some function with with this form. What is this? This is my input, and this theta is some parameters. So this function relates input to the output. It has certain parameters, and now our job is to learn these parameters from the given data. Okay. For example, if we assume a function y is equals to wx plus b. This is my weight, this is my bias. So these are my parameters. How to estimate these parameters? Right now I don't know, but maybe I write it like this: mx plus c. This is the equation of line. And from our high schools, we know that if we have two simultaneous equations, I can get the value of m and c. So this was a very simple example, but in real world, we will have many such data points. This is just for two data points. If I have 2 points, I can use the continuous equations and get the value of m and c. But in real world, we have many such data points, and we need an algorithm to find the parameters. Okay. So let's say, um, so our approximation of the relation between x and y is called as model. This is what we need by a model. This is an approximation of the relationship between x and y. Like, what will be the value of x which can give me the closest or the best value of y. If I talk about the rainfall values, what will be the closest um, input values, how they will be related, so that I can get the exact rainfall prediction. Okay. And for that, you can have this relationship. This is um, logistic um logistic regression, the linear regression, and this, or any other function of your choice. So this is about data, this is about model, and then we need, in all the above cases, we have W, which needs to be learned from the data. Okay. Now, how to learn these parameters? So we need to have a learning algorithm which can help us in learning all these parameters automatically. Okay. And how to say that this algorithm is good algorithm or a bad algorithm? For that, we have the optimization, objective function, loss function, or error function. So now, what should be the goal of this learning algorithm? That when should we say that parameters that I have learned are good or bad? So this error function will help us in identifying whether the parameters which I've learned are good or bad, because the learning algorithms aim to minimize the error. Okay. Now let's take an example of a movie again. So here the data is movie, and it can be movie characteristics like who is the actor, director, story, and other parameters. And y is just a number whether I like a movie or I dislike a movie. Okay. Now here I'm taking this sigmoid activation function 1 upon 1 plus e raised to minus w. Okay. So what is this? This is my x, this is my y. And what is my objective? We want a y, we want this y hat to be as close as this y. Okay. So this y hat minus y should be as small as possible for all the training examples. So suppose I have n such examples and this length is m. Okay. So this is our approximation which I am taking, the probability of liking a movie on the basis of W parameters. How to learn these parameters we will see in coming slides using gradient descent. And what is my loss function? This is my loss function. That I want that this difference y hat, my approximation, and the original y, this difference should be as small as possible. Okay. And there is one thing why we have taken this square, because suppose y hat, the one which our model has predicted, is 0.5. The original value of y was 1. So the difference would be 0.5. In another case, suppose I have 1.5 and this is y is again 1. The difference will be, this is minus 0.5 and this is plus 0.5. If I add all these errors, okay, it will cancel each other. Okay, that's why we always take a square of the error, because the difference is only of the 0.5. So they should not cancel each other. And also the square function is a smooth and differential function. Why differential function is required, we will see in next coming slides. Now the learning algorithm should aim to find parameters which minimizes the above function or the loss function or the error. Now, how to learn these parameters? How to learn these W's or the weights? So, keeping this supervised ML step in mind, we will now focus on this model and discuss an algorithm for learning the parameters. We have two types of parameters. One is weights and another one is biased. Okay. This sigma is my sigmoid activation function, or I can say that this is the sigmoid neuron. Now, for the ease of explanation, I am considering that right now I have only one input and one output. Okay. That means I am only deciding whether I will go and watch a movie or whether I like dislike a movie only on the basis of actor. Okay. Yeah. And we are predicting the rating here. Like what would be the rating? So y here is the real number. Now, what is the input for training here? So input is the n pairs of x comma y, like actor or maybe the story and rating 3.5, or story something and rating 4, some other number and rating maybe 7. Okay, so this is my input. I have n such pairs. I have n such pairs. Okay, and what is our objective? I want to minimize the loss. I want to learn weights and bias such that it helps in minimizing my loss. Now, what do we mean by training a network? So, how to train a network first? Let's start with a random guess. Let's suppose W is 3 and bias is minus 1. I would know whether these parameters W and B are good or not. So here I am considering only two examples. My n equals to 2. And what are those values? X is 0.5, y is 0.2. Another x is 2.5 and y is 0.9. So here I am only considering two examples. Now I want to estimate the value of W and B such that my loss or error becomes close to 0 even if it is not 0. How would I do it? I will start with a random guess. Suppose I have taken W equals to 3, B equals to minus 1. Okay. So let's see how to calculate the loss. So this is my loss with respect to these parameters. I is equals to n. This is my original value and this is the approximation. And what is this approximation function I am taking? How I am linking the input and output? So this approximation function is 1 plus e raised to power minus wx plus b. Okay. If I substitute these values, it will be 1 plus e raised to power minus 3x minus 1. Okay. Now substitute the value of x. For x equals to 0.5 and for x equals to 2.5, we will get the value of y. So let's expand this. I have two examples. I will expand this equation. So I'm calling it as y1 f x1 whole square plus y2 minus f x2 whole square. I'm just writing it down. It will be around 0.9 minus 0.99 whole square plus 0.2 minus 0.62 whole square, which is 0.099. Okay. Now this is okay. I will again try with another value of W and B. Again try to find out loss with for these two values. Suppose next time I take a random guess, I take W equals to 0.5 and B equals to 0. And then again I calculate the loss with respect to W and B. So can anyone tell me how many times I have to do this and see whether this loss is uh, smaller and smaller? It can be infinite number of times because I'm doing the random guess. I'm just trying a random guess and see whether my loss is decreasing or not. And out of all this, the minimum loss corresponding to minimum loss, I will pick W and D. Okay. So it, this algorithm or this approach of random guessing is not feasible in our real world. Okay, so let's see if there is a more efficient and principled way of doing this. So let's start with the gradient descent, which provides us a better way of learning these parameters instead of random guessing. Now let's start by setting up things. We will define some notations and some parameters, and from there on we will try to come up to the algorithm. Okay, so my parameters in this case are W and B. What I'm going to do these parameters, I'm going to put them in an array or a vector and call that vector as a theta. So theta is my list of or vector of all the parameters. And in this particular case, theta belongs to R2. Why R2? Because there are only two parameters, weight and bias. It's a 2D vector in this particular case. Now, what I want to do is, initially I don't know the value of W and B. So what I do, I start with the initial guess. I take some initial value of W and B. Okay. And once I start with this random guess, I want to uh, do some changes in this parameters so that I land up in a better situation. What I mean by better situation, that means I get a less error. Okay. So this so I want to take theta. I want to take this is my small change in theta. So if I make this small change in my theta, I will get a better value. I will get a new value of theta. Okay. So this is my delta theta, which is a vector, which is also a vector of R2. Now what I want to do, I want to move in a certain direction so that I get a theta new. Okay. So now I know what is my theta, but I don't know about this delta theta. Like in which direction I should move so that this theta new gives me a better approximation of my function, or which gives me a less error. I don't know about all these things. Okay. Achha, one thing here which is need to be understand is that whenever I am moving, whenever I'm adding this delta theta, or whenever I'm doing any changes in this theta, I'm getting this new theta, but I want to be conservative. That means I want to move only small amount. I want to move only in a very small amount. So this is called as eta, the step which I want to take. I want to move, I want to get a new delta new theta, but in a smaller amount. I want to move in a smaller amount. Now, what is this right delta theta to use so that I can get a better approximation and I make sure that I'm going in a right direction and not in a wrong direction? Because it may be possible that this theta, delta theta, if I add this into my theta, it can give me a more error. So how to decide whether in which direction I want to move? Whether I, so the answer to this is opposite to gradient. That I always want to move opposite to the gradient so that I get a better approximation of my function, or I always get a less error. Okay. And how I get to know how I get this answer opposite to gradient? So the answer lies in the Taylor series, which we will discuss next. So, so right now, um, let's take this delta theta as u, which is a vector in R2. Now this is my Taylor series. And what is my Taylor series? So the Taylor series tell me that if right now I am at a certain value of theta, and if I want to change that value a bit, then what is going to be the new value? Okay, so this is the change in the current theta value. So what will be the new value? So this will be obtained using the Taylor series. So let's understand what these each value means. So L theta, what is this L theta? This is my function with respect to W and B. Okay. And before understanding all these Taylor series equation, let's understand the basic concepts of what is the derivative. So suppose if I take example loss W equal to, with respect to W, wait, suppose this is my relation. If I want to take the derivative of this function, derivative of this L, it will be dl W upon dW. So derivative with respect to W, it will be 2W. Now suppose I have this loss depends, is a function of not only weight, but it is a function of bias as well. Okay. And suppose this is defined as W square plus B square. In this particular case, what I need to do, I have to take a partial derivative. So this is my partial derivative L with respect to W. It will be 2W. Partial derivative of L, which is a function of W and B, with respect to B will be 2B. Okay. Now what is this gradient? The gradient is, if I ask, the gradient is all these two combined. So partial derivative with respect to W and partial derivative with respect to B. Putting this together in a vector form, this gives me gradient of gradient theta. Okay. So this quantity here is this. Okay. And this, what is this U? U is nothing but this delta theta. Now, what is this value? This is my gradient of gradient. So if I want to write it, it will be something like gradient WB, gradient of gradient. So it will be something like this. It will give me a matrix of 2 cross 2. Okay. Now here, what is this eta? Eta was the small change which I want to make in my original parameters W and B. So this eta is very small. This eta is very small value. Okay. So what we do, if this eta is very small value, this eta square, eta cube and so on will be very, very small. And what we do with these small values in mathematics, generally we make them zero. We ignore them. Okay. So after this, we are only left with this particular part. Okay. Now let's again understand it. I can call it that this is my old loss, and this is after doing a small change in my original parameters, I will get this new loss. And what I actually want, I want that this new loss should be smaller than this old loss. Okay. So I can say that this new loss minus old loss should be less than 0. Okay. This should be smaller. Or I can say, if I bring this quantity here, so if I write it like this, theta plus eta u minus, so we are left with this. Okay. So if this quantity is 0, that means this quantity, since eta is very small, I can write it like this. This is a scalar quantity. Okay, it's a positive, we are taking it as a positive value which is very small. So I can say that this ut and gradient of my loss is also less than 0. Now, okay, so we have this value left. Now, what we want what is the range of this ut, because we are trying to find u such that this quantity is very, means where we should move, in which direction we want to move, so that our new loss is less than the previous loss. Okay. So how to get that direction, where we should move? So let's see. This is my dot product. So let B be the angle between u and gradient of L, theta. So I can write it like this. Now what we want this to, if I do some substitution, I will finally get this value. Now what I want to make this as much as negative as possible. As much as negative as possible means very small amount of loss. And what should be this value? This value should be 180 degree, because The cos beta lies in between -1 to +1. If I want to make this as negative as less as possible, so that this value is overall loss is less, then the direction should be 180 degree. So we can say that u, this delta theta, or my u, should be such that it is 180 degrees to the gradient. Therefore, we can say that whenever we are changing or updating the weights, we should always move in the opposite direction to the gradient. And that is the whole idea of our gradient descent algorithm. So the gradient descent algorithm says that the direction u that we intend to move in should be 180 degree with respect to the gradient, or we always move in direction opposite to the gradient. And what is the gradient? It is always the slope. Okay. So if I this is my parameter update rule. So what we have written is that I should update the weights in such a way. We will come to this again later on. So this is my gradient descent algorithm. I am considering the minimum loss, and I'm considering that after 1000 iteration, this will be very loss. Error will be very less. Okay. What I'll do, I will update the, I will change the weights in a small amount to my current weights and get the new weights. And I will keep on doing this so that my error will be very, very less. This instead of 1000, it can be convergence as well. But here I have taken a very higher value that after these much iterations, my error will be almost close to zero. And what I have said, that in which direction we have to move, how we have to update our weights, we have to always move in the direction opposite to the gradient. And gradient means the slope. So we always move in the opposite direction. So here, this is my negative slope. So I will always move towards the right side. And I am here. So we can decrease the value. We can decrease the error by moving in this direction. And this is generally called as a global minima. Global minima means where the value of error is almost zero. Okay. So this is how we update our parameters. So this is what is the intuition behind the gradient descent, and what is the need of gradient descent. So why we need gradient descent? Because we need to update our parameters. We need to know the parameters, which gives us a better approximation of the original values, so that our error can be less. So that is the major intuition behind the gradient descent. And how gradient descent works, it as the name suggests, descent means in the direction opposite to the gradient. So it makes sure that we are going in the right direction, and we are going in a direction that will help in decreasing our error and give a better approximation. So this is all about in this slide. If you have any questions, you can ask.
Dr. Bansal, there are no question ahead.
Yeah, okay.
Thank you so much, Dr. Bansal, for the insightful session. We hope everyone enjoyed and gained valuable knowledge. A big thank you to everyone who enjoyed us today. It is gained valuable knowledge. A big thank to everyone. Remember to like, share, subscribe, and hit the bell icon button. Update on our upcoming event. Have a wonderful day. We look forward to seeing you next time. Thank you.
Thank you.